So this talk will be a bit in continuation with what Katja just presented. It will be a bit deeper in in two specific topics that Katja touched, that there are synchrotron radiation and Faraday rotation to probe magnetic fields in our galaxy. For most of you, these data, I guess, will be new. So this is the main goal of my talk, is actually presenting rather new data. Some of you already know, because I know they already listen to my talks. But for most of you, I think such data are really new and provide a new perspective on the diffuse interstellar medium as we used to know it. This work, most of the work I'm going to show has been done in the last couple of years. It was part of a Marie Curie program that I worked in Zagreb, in Croatia. So most of the group here is made of Croatian people, but there is a list of people that contributed a lot to what I'm going to present, and of course to the LOFAR collaboration. So the main character is LOFAR. LOFAR is a young instrument. It started in 2010, so it's almost almost a teenager. And it's a wide network of interferometers all over Europe. Basically, it has two sensitive channels, one between 100 and 200 megahertz, and one below 100 megahertz. For most of the talk, I will focus on the HBA channel array. And for most of the talk, since I'm going to focus on the diffuse galactic emission, basically all stations we used are only the Dutch stations, the very compact configurations, but that gave us angular resolutions of about a few arc-minutes in the sky. But in principle, with LOFAR, you can go very deep in resolution and go to sub-arc-second scales. It's very interesting what will be published in a few years from now. So something already has been published. It's the LOFAR 2-meter sky survey that will eventually cover the full northern sky. Right now, there are two main fields of view that have been published. There is this central field of view at about array deck 180, 30 degrees, and around zero, about 20 degrees. And I will try to give you a flavor of this data set. And as a teaser, this is the kind of data we are working on. Okay, so here you have a video that I hope in the rest of the talk you will kind of understand what you're looking at, that is showing polarized intensity at very low frequencies, below 200 megahertz. So basically, it's polarization from synchrotron. That is seen over very wide sky areas. You see the size of the moon in comparison. And I will try to highlight some of the main features. But you see these gradients that we see in polarization as a function of the quantity that I will clarify in a bit. So, and that is connected to the Faraday rotation that the synchrotron radiation is experiencing. So this is a very short teaser. In practice, I want to put in context a bit more these kind of studies of diffuse synchrotron radiation in the galaxy, in something that Katja just mentioned at the very late stage of a talk, that is trying to understand again, and here I link with the first talks of the week, trying to understand this multi-phase ISM and how phases talk to each other. This is a very simple, simplistic picture where we want to understand how the very hot and diffuse medium condenses and cools down to regions where actually star formation can actually go on. And this kind of old picture now has become more turbulent and messed up. So if you follow the talks by Patrick and Benjamin, now it's clear that these phases talk to each other in a very turbulent medium, where turbulence is not just a result of buoyancy due to stellar feedback, but must include also very large-scale motion, as Patrick pointed out. All of this is complicated by the presence. This sequence of phase transitions is actually complicated by the presence of cosmic rays and magnetic fields that clearly shape the structure of the interstellar medium. And this is something that we have started in the, I would say in the last 10 years, really to tackle from observations. And the Planck satellite helped us to step forward in this kind of analysis, but not only the Planck did. So one of the main, as Katja pointed out, one of the main and historically the oldest way to probe magnetic fields is really synchrotron. And this is almost direct probe of the fact that there are magnetic fields, because you need cosmic ray electrons that gyrate around magnetic field lines to see synchrotron. So if you see synchrotron, you know that there are magnetic fields there. And the emissivity is function of the energy of the cosmic rays, and the magnetic, as Katja pointed out, the magnetic field perpendicular to the line of sight. And because of the beaming of the synchrotron emission, it has a very high linearly polarized light, up to 70% here in theory. In practice, we never observe, or very rarely observe, such high linear polarization in synchrotron, because the magnetic field in synchrotron must interact with this soup of multi-phase gas somehow. But the main message I want to give you, one of the main messages, is that through the interactions between synchrotron radiation and the multi-phase interstellar medium, we can actually learn something about this multi-phase ISM. And one main feature is really Faraday rotation, and this is what Katja already presented, is is a process that affects linear synchrotron polarization because of the interaction of these polarized light with magnetized and ionized gas along the line of sight. And as Katja said, it's a frequency-dependent process. It goes with the square of the wavelength. And here you can see a demonstration of that. So here you see the whole sky with the galactic plane running in the middle in galactic coordinates, polarized intensity at 20 gigahertz and 1 gigahertz. So you can see that something is going on towards the inner galaxy here. So the two images clearly differ, and this is mainly the result of Faraday rotation along the line of sight. That is, the net effect is a net depolarization. We cannot detect the polarization that you can see at higher frequencies because of Faraday rotation. So Katja already showed these images that shows the schematic process of Faraday rotation. Something I want to highlight again is the fact that the rotation of the polarization plane is connected to physical quantities, okay, to the electron density and magnetic field along the line of sight, magnetic field strength along the line of sight. It can teach us also on the direction in this case, if it's positive or negative. It can tell us if it's pointing away from us or towards us. And the rotation measure enters as a phase shift to the Stokes parameters that we actually measure. Okay, so this is the measured quantity, and somehow we need to associate we need to disentangle the rotation measure from these, invert this equation and get the rotation measure. And from there, from these kind of simple assumptions, from these kind of measurements, you can build rotation measure grids, as Katja showed. So each point here is an extragalactic radio source. You can measure its polarization. You can measure at different frequencies. You can measure the rotation measure, and you get these large-scale patterns in the sky that must be associated to the structure of the magneto-ionic medium in our galaxy. People did something more fancy and tried to reconstruct since in the previous image you're stuck with discrete measurements. They tried to do some Bayesian reconstruction of the continuous rotation measure profile of the galaxy, and ended up with maps like this that have been used to study the structure of the magneto-ionic medium. Something I want to point out that some of this structure clearly correlates with traces of ionized gas. This is H alpha that depends on the emission measure on the square of the free electron density. And if I blink the two images, you clearly see structures in both images. But you also see structures that are not in H alpha. And this is clearly related to the fact that the rotation measure is a convolution of both thermal gas and thermal electrons, sorry, and magnetic fields there. Now, in practice, reality is more complex. The galaxy itself is a synchrotron emitter. And so even the synchrotron polarization of our galaxy will undergo Faraday rotation. And so the way we try to characterize these more complex process is by introducing a quantity that's called Faraday depth now, that has exactly the same units and form as rotation measure. But in practice, conceptually, it's like a specific rotation measure along the line of sight that is produced because of interaction of synchrotron and Faraday rotation in our galaxy. So the idea here is, do we have any mean to reconstruct the complex structure of the magneto-ionic medium along the line of sight? So bear with me, this is the last a bit technical thing. This technique exists, and it's something that has been developed in the 60s, 70s, but only applied very recently in the early 2000s. Well, very recent, where that is called rotation measure synthesis, and that allows us to do this kind of Faraday tomography, some tomography in space of the magneto-ionic medium. The general idea is that we measure the Stokes parameters, and as you see, because of Faraday rotation, we get this modulation of the Stokes parameters as a function of lambda square. Now, imagine you had a sinusoidal, okay, of this function of this fluctuation was exactly a sinus wave. Then, if you would do a Fourier transform of this signal, you would get a specific peak, a specific mode that would excite this Faraday rotation pattern. And the general idea of rotation measure synthesis is really the same one. So you do some kind of analog of Fourier transform of your data that converts the polarized intensity function of lambda square, that is the observed quantity, as a in a quantity now that is polarized intensity as a function of the Faraday depth. So now this is a physical quantity. This tells you about the combined effect of electron density on one hand and magnetic fields. This is an actual line of sight of LOFAR, okay? And so for this line of sight, well, we identified two principal modes that produce Faraday rotation for this diffuse polarized emission. So possibly two cloudlets of magneto-ionized gas. The interpretation is more complex than that, but this is the general idea behind Faraday tomography. You end up having these hyperspectral cubes that you can treat as spectroscopic cubes. So eventually you can compute moment 0, moment 1, moment 2 of these spectra. And then now I hope you understand a bit better what I was showing at the beginning, the video. We were just going through these spectra that you can compute for each line of sight in your field of view. Now, something very important to highlight here is the width of these lines. They are deeply connected to the frequency range you're sensitive to. So if you change by an order of magnitude your frequency, your observational frequency, you change of 2 orders of magnitude the ability of resolving structures in Faraday space. So you see the jump that we get by observing a very low frequency with LOFAR comparing to what you could still do Faraday tomography at a high frequency at about 1 giga, but you would get a resolution in Faraday space that is very, very large. And the point here is that if we put numbers together, the multi-phase ISM I showed at the beginning, well, you end up with values of rotation measures that are a few radians per square meter. And this is where the low frequency range in observations is gold, because it allows us to access very small scales in Faraday space in this column of ionized gas and magnetized gas. So here, for comparison, you have the 1 radian per square meter resolution in Faraday space that we have with LOFAR. This is this is actually green, but here is black. Anyways, this is the SKA low that will be eventually obtained with SKA. But you see, with NanoFAR, we can already reach an order of magnitude better resolution in Faraday space than we have with LOFAR. And then here you see what you would get at about 1.4 gigahertz with, for example, the Jour telescope in Canada. So this is the power of Faraday tomography at low frequency. And now when I show you this image, I hope there is something clearer. And we see polarized intensity as is shifted through Faraday depth in practice. And you see a lot of different structures. You can compute the 0th moment. And here you see the kind of morphology we're dealing with. You see the size of this field of view is very large. And you see very coherent features in this particular field of view where you have coherent intensity feature in polarization, but also very coherent depolarization features. These depolarization features, these black features, are called depolarization canals. In the regions where you see no polarization at all at any Faraday depth. Okay, so these are regions where there is complete depolarization along the line of sight for processes that we may discuss, but they are not completely understood. You can also compute the first moment. So you compute the mean Faraday depth weighted on your polarized intensity, as you would do for the spectroscopic cubes for the first moment, the mean velocity weighted on the brightness temperature with LOFAR, and you can compare this value with the maps I've shown you at the beginning, what you get from extragalactic sources. This map is tracing the full length of the line of sight from you to the extragalactic source. Well, this one is tracing Faraday rotation happening inside our galaxy, okay? So there, in this specific field of view, we see overall correlation of some regions. You can see more details in this paper. But of course, there are regions that do not correlate. They better correlate at higher frequency, but not at this low frequency. This is showing a complexity also probing different, most likely different volumes of magneto-ionized gas along the line of sight. And something that we have started to do with LOFAR, since we have this very high sensitivity in Faraday space, is trying to understand the connection with the other phases. So we started putting together the polarization seen by LOFAR with traces of neutral gas. And here, this is what I've shown. I'm showing you where orange is LOFAR polarized intensity at a specific Faraday depth, and bluish is brightness temperature of neutral hydrogen, a specific velocity in our galaxy. These two, what we found is that these two, and then here you have drapery pattern, actually tracing magnetic field on the plane of the sky through dust. So it's another magnetic field projection, a plane of the sky versus line of sight, if you want, and possibly another tracer, because Faraday rotation is happening in very ionized gas. Or not, this is a question. But so what we found is that these data set, in particular H1 data in these fields of view and LOFAR polarization, do correlate morphologically. Their gradients are statistically aligned. And this is shown by these metrics, and where basically, if you have bright colors, you have alignment of the morphology in the maps of brightness, temperature, and polarized intensity. And we did this as a function of Faraday depth and velocity. So you see that there are clusters, okay, of regions where in Faraday space and velocity space, they do correlate compared to other regions where there is no correlation at all. And we also try to investigate which phase traced by H1 gas. You know, it's just at the end, it's just a matter of the spectral width of the lines. If it's very narrow, it's most likely cold gas. If it's very broad, it's most likely warm gas. And most of the correlation we found is driven by the cold phase of the H1, traced by the H1 gas. This is open questions because I've told you Faraday rotation is coming from ionized gas somehow. Of course, here there is also synchrotron involved. So it may be associated to the actual synchrotron emission that we're seeing. So these open questions and also need for models. This is tough because you need to model a lot of processes at the same time. This is something that we have started to do mostly with Marco Padovani and Eva Durmusi in the last years. And here, as an example, we try to do mock observations of what LOFAR would see of a typical feedback process in the ISM, where you have to shell colliding and forming cold gas at the interface of these warm phases. Of course, the first approach we have is very if you want, we need to use a lot of approximations. First is the distribution of cosmic rays. These simulations were not the best to treat all these physics inside. So we did a lot of post-processing. We needed to include some Sierra physics and some physics for the ionization processes. In this case, it's just post-processing, assuming chemistry, steady state chemistry. We used some kind of analytical approach in there. But anyway, anyhow, we had all the ingredients this way to have ionized gas, to have synchrotron radiation, and produce the kind of videos I've shown you before for the observations, now for simulations. So you see gradients again that are related to the mean magnetic field structure in the simulations, and you see a lot of different morphology that we are now studying in more detail and comparing with simulations. Sorry, with observations. But the key point of this work at the beginning was, well, in the simulations you can have access to the actual phase. You know where the hot, warm, and partially ionized or partially warm gas is, so you can say where the Faraday rotation is coming from and synchrotron is coming from. Long story short, we did similar studies that we did in observations. So we used also mock observations of H1 and produced the same kind of correlations. And you do see that we find correlations that do depend on the mean magnetic field that you're seeing. So projection effects play a crucial role here that may also guide the interpretation of what we see in different fields of view in the sky. But the main difference from observations is the lack of correlation with the cold phase. With the cold phase, because here you see there is no clustering velocity space. The main reason is that the warm phase has very broad spectral lines. So basically here we're seeing that most of the correlation is coming from the WNM, basically. That makes sense because it's more ionized than the CNM, if you want. So let's say our simulations are more intuitive in the interpretation than actual observations, and these open questions, because we start having data or LOFAR data even towards colder regions in the galaxy. Not the field of view I've shown you is intermediate high galactic latitude region where column density of H1 goes up to a few 10 to the 20. Right now, we have data towards local nearby star-forming regions like the Taurus and Perseus Cloud, and you see that there is a lot of polarization that distributes along these molecular complexes. And again, this is polarization as a function of Faraday depth. So it's polarization that is affected by Faraday rotation, by ionized gas. What are we seeing here is still an open question. It's all still preliminary. It was preliminary last year to those who already saw, but this year I became father, and so I did proceed very fast. But again, this is the first time, for example, that we see these regions at these frequencies, and it's showing a completely new sky. Okay, and we need to understand what we're seeing here. Okay, and something interesting in this field of view is that you can compare with the same data sets I've shown you before. And if before overall we could find correlations, in this case we clearly see that the Faraday depth we are tracing with LOFAR is completely different. Here it's negative, here it's positive. So magnetic field have a different direction in these fields of view. Here it's positive, here it's negative. And here this is positive and this is negative. So here we are clearly seeing a different volumes in the galaxy when it comes down to magneto-ionic medium compared to the previous field of view. So this shows that depending where you're looking in the sky, what you're seeing in the magneto-ionic medium may change drastically when you see at high frequency, at low frequency. Finally, I want to show you a last field of view that was recently compiled. These are large mosaics, so it takes time to produce this kind of data set. And this is a beautiful image produced by Loborka Gajewicz, that is now PhD in Hamburg, that is showing polarized intensity as a function of Faraday depth beams. And you see a huge gradient in Faraday depth. This is very consistent. This is going from negative to positive Faraday depth, and it's very continuous. This must be related to the magnetic field geometry over the sky, and you see over tens of degrees in the sky. And the beauty of the patterns and texture is really incredible. And of course, we need to characterize the differences of these patterns and textures between different fields of view in the sky. I reached my conclusions. My point here, my goal was really to present new data that we are starting to understand, but still there are many open questions. These trace, yes, diffuse ISM, but we start having data towards denser regions that are more interesting for people working in star formation. We need more models or to refine models, actually, to fine tune to this kind of problems. And all of this will prepare for, of course, for the SK. But in practice today, we have already a lot of instruments in the northern hemisphere that can help us understanding the physics of synchrotron at these low frequencies. And particularly, we're very happy to have an accepted proposal for this winter with NanoFor. So I finished, and if you have questions, I'm happy to answer. And I leave you with this advertisement of, if you're interested to these topics in December here at PNS, we will have a 2-day workshop about revealing cosmic magnetism in the near future through Faraday rotation. So registration are open, and if you want to submit abstracts, you're more than free to do that. Thanks.